Hi everyone, Professor Gassimi here. In this component of the lecture, we'll be discussing logistic regression. Now, to set the stage, let's think about the classical regression problem. We're interested in identifying a relationship between one or more inputs, we often refer to as X, and one or more outputs, we often refer to as Y. So let's say that we have a very simple example where we're interested in, given the age of a person, predicting something about the height of that person. Well, all models start off by making an assumption about what the nature of the relationship is between the input variable, in this case the age, and the output variable, in this case the height. And so we might, for example, choose a model with the assumption that this relationship can be approximated by a straight line. And if we did this, we would be performing a linear regression. Now, machine learning is the use of techniques that leverage the properties of the data set to solve for the most optimal value of the parameters. In the case of a linear regression, that's the slope of the line, so m in the equation, and the intercept of that line, which is b. So the machine learning paradigm is to sort of search around, figure out exactly how you adjust those two parameters so that you do the best job fitting the line. But anytime we use a word like best, somebody could ask you, well, what exactly do you mean by best? How are you measuring specifically your performance for the fit? Now, the way that performance is measured in the context of machine learning is through something called a loss function, okay? And usually what you're trying to do is to minimize that loss function, okay? So for example, in a basic regression task, one loss function we might use is called the mean squared error, or MSE. And let's look at this equation together so it's very obvious exactly what it's producing. This says, go through each of your data points, 1 through n, that's each of the blue points here on the line, and go ahead and take the difference between what your model predicted, YIP, that's indicated by this line, right? So everything along here is a potential YIP. But specifically, go to those points in the line where I also have some real data, YI. Okay, well, here's a real data point, YI, and here's the corresponding value right underneath it, a YIP. Take the difference between those two and square it and sum it up across all the points. Now, why are we squaring it? Well, because we wouldn't want this value down here, this -1, to cancel out this +1. So the use of the square is just a simple way to make sure that we don't have those two conflicting. There's a little bit more nuance to it as well, which we're going to speak about here in a minute too. Effectively, though, that error function, the mean squared error, looks something like this with respect to the difference between your predicted value and the actual value. So as you move further and further away from the optimal value, you get this effectively exponential increase in the error that's incurred due to that change. But recall that these measurements of error, there's nothing special or unique about them. We can define a different measurement of error between what our model output and what existed in reality. So for example, instead of the mean squared error, which is sometimes referred to as an L2 loss, we could alternatively choose to define the error as the mean absolute error, shown in the equation here below. Now, let me go ahead and step you through this equation. Just like before, we have n data points, that's each of the points that exist here on the right-hand side, 1 through n. What I'm interested in doing is summing up the difference in the absolute value between the real value, so for example, on this point, this is the real value, and whatever I predicted at that real value, which is this point, okay? And the difference between this L1 loss, or the mean absolute error, and what we saw previously is that we have an absolute value symbol here to take care of values that are sort of beneath the line, not canceling out the values that are above the line, instead of using a squared term. And so if we were to plot what the error looks like as a function of the deviation between the prediction and the actual value, what you see here is that there's a linear increase in the effect, whereas before we had an exponential or squared increase in the error as a function of the difference between the predicted and the actual values. Now, if we look at these two side by side, you can sort of appreciate those differences more. You can see here, for example, if you look at the scale of the y-axis, that as we start stepping away, this error really starts to explode relative to the linear increase in the error that we see when we're using an L1 style penalty. And which one is correct really depends on what it is that you want to accomplish. So let's say that you had some data and this data was corrupted by outliers. Well, what you might want to do is prefer to use an L1 style loss function in that case. Well, why is that? Because L2 is significantly more sensitive to errors, right? It grows, the penalty that it pays grows exponentially as a function of that error. And so L2 is more likely to be yanked, as I'm showing in the example there on the right-hand side, in the direction of an outlier than an L1 optimized regression might be. But that doesn't mean that L2 doesn't have important uses. In fact, the sensitivity of L2 to outliers is useful if you suspect that the outliers provide some kind of important information for your classification purposes. I bring these things to your attention because the most important thing for you to understand if you want to design an extension, a novel extension or method to a classification model, is intuitively why or how those classification models work. So you could, as an example, come up with a new notion of what that error is and demonstrate that it's optimal for some particular kind of problem that you're interested in, more optimal than using the out-of-the-box technique, and that would be a methodological contribution. There's obviously some subtleties to this and some details that we're not covering in the lecture yet, but in spirit, if you can understand what the objective function or the loss function of a model is and what the form of the model is, those two things together will give you a very solid idea of how it works and what to expect of it. Okay, well, we spent the last several minutes speaking about regular linear regression, very simple linear regression. But the problem with the linear regression was that regardless of the loss function we chose, it seems that it's just not a good model for the problem that we wanted to solve, because height doesn't continue to grow linearly with time. After we get to a certain age, we actually shrink a little bit. And so the problem with a model that's linear is that the errors on these individuals who are in their adulthood or their elder years is really high. That provides some indication that the form of the model, of this particular parametric model, may not be the best one for the task at hand. What we'd really like to do is be able to take something like a line, but then bend the ends of it so that at some point it kind of flattens out and saturates. That would solve our problem in this case. If we wanted to saturate, what we're really interested in is a sigmoid. And I'm showing the equation for a sigmoid. What I'd like to do is step you through it so it's not mysterious. The A term in that equation just says, where do you want the sigmoid to saturate? The mx plus b term is the exact same kind of guts that we had in the linear regression. It says that we want, as x increases, we want it to have a pull on the outcome according to the slope as well as some intercept term. And then the e to the minus power of mx plus b is a force that tends towards zero as x grows more positive, and towards negative infinity as x grows more negative. And so, well, what will that do? Well, that means that when x grows more positive, what is y hat going to be in that equation? It's just going to tend towards a. And when x tends towards negative infinity, that equation is going to become 0. So what you end up getting at the end of it is a line that looks like that, which is similar to the straight line, but we bent it so that it saturates as we had intended. And that's really essentially all a sigmoid does. It bends the line for you nicely. Now, when we think about binary classification, or logistic regression, I should say, in the case of this particular model, we're usually not interested in values of a other than 1, because binary classification is choosing between two values. And if a sigmoid stretches between 0 and 1, that very conveniently spans the whole range of a probability. So for example, I might be interested in coming back to text classification. I might be interested in understanding whether a sentence is happy or not. And I might be interested in trying to figure that out by using the count of the exclamation mark characters within it. Well, I could collect some training data and include that as these single dots that you're seeing here. And then my goal would be to sort of fit this line so that for a new dot that shows up, I could do a good job having this line as close as possible to 1 in the case that it's 1, and as close as possible to 0 in the case that it's 0. There are some things that I want to point out here, of course, that notice that in this area here, where there's examples of both 0s and 1s occurring for the same value of x, the sigmoid sits somewhere in the middle to reflect that relative probability exactly as it should. And as a function of the number of exclamation mark characters in the sentence, we start seeing a saturation in the classes being happy. The sigmoid also sort of reflects that. Now, just like a linear regression, the value of the parameters m and b in the equation below are determined by minimizing a definition of error. So we have to say, what exactly are we going to consider to be the error so that we can tune the m and the b values, tweak those knobs so that we can minimize that and get the best fit possible. Well, in the case of logistic regression, that error function is referred to as cross-entropy loss. And to understand what cross-entropy loss is, let's try to remember first that what our model is actually doing when it predicts y, which has two possible states, it's actually really only predicting one of those states, right? It's predicting the probability that y is going to be equal to 1, not the probability that y is equal to 0. Now, fortunately, because there's only two states, if I know what the probability of y equals 1 is, then I can figure out what the probability that y equals 0 is by just taking 1 minus that, and I can have both values. Okay, so this statement, this if statement that I wrote here, is equivalent to the statement that I'm showing here. This simply says, if y is equal to 1, then this term on the left, the estimate that comes from our model, will exist, but the 1 minus y that you see here is going to set this term equal to 0, and anything to the power of 0 is 1, so this term goes away. And similarly, if y is equal to 0, this term now goes away, and you are left with the 1 minus y. Okay, well, why do you need to do that? Because if you want to assess the performance of your model on several data points, you need to be able to kind of be speaking with respect to the class of interest. So let's think through an example here. Let's say that we have the red point there, which was y equals 1 that we wanted to classify. Well, what's going to happen then is we can take this point y equals 1. We can look at our function here and say, what was the predicted value of y hat? And we can get the probability of that and move on. But if y was equal to 0, in this case, we actually don't want, the probability of happy. We want the probability of sad, which is, let's say, 1 minus that, or not happy, which is 1 minus that. So we would take this point down here, which is precisely what the equation is attempting to do. Okay, now if you wanted to figure out across all these data points for some setting of your parameters, let's say the M and the B are, we're going to refer to those as a set of parameters that are in theta, and we want to find a setting of those that maximizes the probability of yi given xi after summing over all of these different data points. If we could do that, if we could sort of make this line fit as best as possible, we would have maximized this value. Okay, so now that you understand the basic form of this equation and why we have these two terms here, one to assess our model in the case that the outcome is actually 1, and another term to assess our model in the case when the outcome is 0, what we're ultimately going to do to assess this is, for every pair of data points, from I equals 1, let's say, through n, we're going to probably multiply those probabilities up to get a way of measuring how well the model fit the data. But multiplying lots of small numbers, which is what probabilities are, can very quickly lead to an issue called numerical underflow. And that's the reason why we always take the log of probabilities when we're going to be doing a multiplication of them. So if we apply the logarithm to the equation, we get what you see there on the right-hand side. And if we want to make this a loss function, so something that's negative instead of positive, we just multiply it by -1, and we now have a loss function. And that loss function is called cross-entropy loss. I think one way to have a better intuition for how cross-entropy loss is applying the penalty is by graphing it. In fact, what I suggest is that if you're ever confused about how a particular loss function works, not just for these simple models that we've been discussing, but for any model that you're going to work with, if you're confused about how to choose the loss function, I suggest that you plot it. What I'm showing you here is, you can see for a given value of y could be 1 or y could be 0. But what this says is that as a function of the predicted value of y1, what's the loss that you incur? So basically, if your actual value of y is 0 and your predicted value of y is 1, you get this very, very high loss. If your actual value of y is 1 and you predict 0, you also get this very high loss, right? But conversely, if your predicted value of y was 1 and your actual value of y was 1, you get very little loss. So plotting these things will oftentimes help you understand how exactly the penalty function works, so that you can either change it or at least understand it. Now, one of the things that's nice about simple models like logistic regression, or any of the models in the regression family, is that the coefficients are easy to interpret. So one of the things you do when you're dealing with logistic regression is compute an odds ratio by taking the exponential of the coefficient value. So for instance, in the right-hand side, if m was the coefficient that described the effect of x on y after being put through the sigmoid, of course, the exponent of m there would tell us the multiplicative increase in the probability of the outcome that is the result from a 1-unit increase in x. Now, there are scenarios, especially in NLP, where the features can be really large. The large availability of features can lead to issues when you're running a logistic regression. Two issues specifically are overfitting and feature collinearity. Feature collinearity happens when two features in your data set are very highly correlated. Let's say that in every sentence you used in a bag of words representation, every sentence that had the word the always had the word cat. And those both happened exactly one time in every sentence. Well, then those two columns in your data set are going to be identical. And so they're perfectly collinear in that. The other problem that can exist is overfitting. This is when you have less or as many rows in your data set as you have columns. If you have that kind of relationship, it becomes very, very easy for your model to overfit. That has a lot more to do with not the columns in your data set per se, but the number of parameters that your model has relative to the number of data points that you have, oftentimes called the degrees of freedom in your model. Now, one way to address these problems is through a process called regularization. That's basically adding a term to the optimization function that incurs an additional penalty for large coefficients and encourages the model to effectively toss out features that are unnecessary. Now, this equation down here is the exact same equation we presented a couple slides ago. It just tells us, hey, here's the function that we want to use. We want to maximize this or find the maximum value of this function by tuning the things in theta. This function tells us how well our model fit the data. And the theta term here is the m and the x parameters in that equation that we mentioned earlier. Well, all we've done is we've added to this now an additional penalty, or a new penalty, I should say, called r theta. So it's a new function of these same parameters, the m and the b. And then we have a tuning parameter on it called alpha that says how important is this r function. There's two popular choices for that r function. The first is called L2 regularization. And just like we saw before, L2 regularization here means that we're going to take a penalty and apply it as a quadratic function of the sum of the values of the weights. And there's an L1 regularization, which, again, as we saw earlier in the case of linear regression, applies a linear penalty as a function of the weights. Now, in both of these cases, what you're going to end up seeing is that the coefficients in the model that have very, very large values, which is usually an indication of overfitting, will get thrown out of the model. And so the regularization here can act to some extent like a feature selection in your modeling paradigm. Now, there are a variety of circumstances where you may need to model more than just two classes. In sentiment analysis, for example, you're not just interested in happy, not happy, you're usually interested in a more nuanced set of classes. Are they happy? Are they neutral? Are they sad? Are they angry? Are they joyous, etc.? And in fact, this exact example that I'm showing on the right-hand side was what we spoke about in the naive Bayes component of the lecture. So let's say that we wanted to solve this problem using the logistic regression framework that we spoke about earlier. Well, the way you do that is with the multi-class version of logistic regression called multinomial logistic regression. And effectively, the only difference between the two is that the multinomial logistic regression uses a generalization of the sigmoid function, which is what we already discussed earlier. That generalization is called the softmax. The zi term here in the equation just refers to that simple linear function, mx plus b, or there could be obviously other features, and that could be longer. And the softmax returns a vector of the probabilities, one for each of the classes that we wish to predict. So in the case of this example here on the right, if we wanted to know the probability of class C, given the data, the softmax would return three values, one for happy, one for neutral, and one for sad. But of course, multinomial approaches may not be optimal in all cases. Consider the problem of trying to classify the age of an interviewee based on some text they've generated. So for example, you get a text transcript that says you whippersnapper, and you've got to figure out something about the age category that text came from. there are multiple age groups, so we could use a multinomial logistic regression, right? This is the same technique we spoke about earlier. We can make baby one group, child one group, teen one group, adult one group, and elder one group, and then fit the softmax function and assign a probability to each of those given the text that we just observed. But the problem with multinomial logistic regression is that it assumes that the categories we're trying to predict are independent of each other. So it assumes that the difference between an apple and an orange is as different as between a child and a teen. And that the relative difference between an apple and an orange, for example, is no more or less than the relative difference between an elder and a baby. And intuitively, we know that that's not true, right? I mean, there is a logical way to order these categories that we have there on the bottom of the screen. You know, a child as a group comes after babies as a group, teens as a group come after children as a group, and so on and so forth. So anytime there is a meaningful way to order the classes, that's when you use ordinal logistic regression. And ordinal classification doesn't have to just exist for logistic regression. It can actually be used in any classification paradigm. And what an ordinal regression in this case can account for and take advantage of is the orderly structure within the outcome target. So how does it work? Well, one of the very simple approaches to accomplish this is to train an ensemble of k-1 binary classification models, where k describes the total number of classes. That's, in this case, 5, because there's baby, there's children, there's teens, there's adults, and there's elders. So what I might do here is I might train a first binary logistic regression model that just says, hey, tell me the probability that the age is greater than baby. So I'm going to split all of my training data and train a model that's just a master at figuring out whether you are greater than a baby or not greater than a baby. And then similarly, I could train a second model that splits the two populations and says, I'm just going to be a master at classifying whether you are above a child or at child or below. And so on and so forth. We could do this for the threshold at the teenager level, at the adult level, and so on and so forth. Okay, now notice that when we do this, again, we train k-1 binary classifiers. You only need to slice this space 4 times to get all 5 of the classes. And we can then identify the probability of a given class by just taking the differences between the probability estimates from the classifiers. So for example, if you wanted to figure out the probability that someone's age was teen, you could take the probability that the age was greater than child over here, subtract from that the probability that the age was greater than teen, and the differences between those two would give you the probability of this class right here.